Part of our webinar series on monodisperse fully porous particles. Geoff Faden, our president and co-owner, will discuss the advantages that monodisperse particle technology has for oligonucleotide separations. My name is Alex Nasseh, and I'll be filling in for Ed today as moderator. If you have any questions during the presentation, please type them into the chat window and include your name and company. We will do our best to answer as many questions in the allotted time slot as possible. If you miss anything or would like to review the content, you'll be able to watch a recording of the webinar and view the slides on our website. We will also send out a follow-up email with the links to those as well. Before Geoff begins, I just wanted to give you a little background on MacMod. MacMod is a chromatography company that offers scientists innovative solutions for their complex separation needs. We recommend and supply the best columns and accessories to our customers. We also provide application notes, technical reports, white papers, and other up-to-date resources from industry-leading scientists to keep you informed. Today's speaker, Geoff Faden, is the president and co-owner of MacMod Analytical. He received his Bachelor of Science in Chemistry from Penn State University in 2003 and his MBA from Temple University in 2014. He has served as a trusted chromatography partner for the life science industry for over 15 years. He has experience working with major pharmaceutical, biopharmaceutical, industrial chemical, and environmental companies to improve their chromatographic workflows and provide innovative solutions to their challenging chromatography-related problems. Thank you for joining us today, Geoff.
Thanks, Alex. Super excited to be here today. This webinar, part 3 in the series, is entitled Oligonucleotide Analysis without ion pairing additives using the novel UHPLC column technology. We partnered with Dr. Kowalska and Dr. Bocian at Nicolaus Copernicus University in Poland to generate this data. And it's been an excellent partnership, and we have a bunch of future work that we're working on. But what I'd like to talk about first is the product name. The name of the product is Evosphere Monodisperse UHPLC particles, particle technology. So I'm going to give a quick review on the technology and essentially the evolution of UHPLC particles from the get-go, or HPLC for that matter. We had irregular shaped particles, so there's a morphology type. Now most particles are spherical that you would buy commercially. There's size has reduced over time. Initial HPLC columns were particle size of 100 micron, and now we're down to sub 2, and I think the commercially available 1.3 is now available. Purity was a point of evolution where you have more metals content over time. You had type A silicas and now type B silicas, which are very low metals content. And that's pretty much the standard that you'll see across the industry. But the innovation that we're talking about here is the distribution of the particle sizes in the column. And what we mention here is this D90 over D10 term. So what you have here in the middle is, or well, let me say this. In the green trace on the left, you have a commercially available, fully porous particle, 3 micron. And you can see that it has a fairly wide Gaussian distribution. And then in the right, you have a another commercially available 3 micron. And even then you can see that the mean particle sizes are different. The Evosphere you can see is a tighter band and is also a commercially available 3 micron material, but this band is monodisperse, and I'll show you how we go to measure that. So we measure it with a Coulter counter. And what you do to measure particle size distribution is you look at the 90th percentile and you divide the count of particles at the 90th percentile, and you divide that count by the count of particles at the 10th percentile. And the closer that factor is to 1, the more monodisperse the material. The commercially available silicas are closer to 1.6. The new material here is around 1.1, and visually you can just see visually how that is different using a scanning microscope. So you might say, okay, cool. So I got a very monodisperse material. What is that? How does that impact my separation? So all the manufacturers show this equation. It's the resolution equation. This is a graphical representation of it. Citation was left off, but it was done by a group, Pete Carr's group of University of Minnesota. And what they do is they break down the equation into an efficiency term, a selectivity term, and a retention term. The major impact that the monodisperse particles have is on the efficiency term. And how do you calculate efficiency? It is the length of the column divided by the height equivalent to a theoretical plate. And you might say, okay, well, what is that? What's the height equivalent to a theoretical plate? So what we show here is the standard Van Dienter equation, where you have your H, which is your height equivalent to a theoretical plate, and then you have your A term, your B term, and your C term. The C term is the resistance to mass transfer. That's how the analytes go in and out of the particle. The B term is your longitudinal diffusion or your molecular diffusion. That's how the band stays together in the column. And then the A term is your eddy diffusion or your multipath effect. That's how the band travels in between the particles in the column. And, you know, this doesn't really go deep into what the math looks like. So that the expanded Van Dienter equation is how I like to show it, because it sort of simplifies what we're talking about here. Well, expands on it and simplifies it, because when you actually see the math behind the C term, they had to account, when they were originally doing it for chromatography, they had to account for gas and liquid. So the gas term goes to 0. And because in small molecules, what we're talking about here, or mid-sized molecules, they transfer in and out of the particle pretty fast. So the really is not that big of a play. So that sort of gets minimized. And then you can say, oh, well, the B term in liquids, it doesn't really diffuse that much. So now you're left with that being minimized. And so you're really left with the height equivalent to the theoretical plate is equal to 2 times the packing factor times the mean particle size. And so what that means is, if you can think about it, you know, and this is coming from another dissolution method, where you can put these theoretical plates in a column, and that is how many you can fit in there is how efficient the packed bed is. And so if you can minimize that packing factor, you can drive that height equivalent to a theoretical plate lower, so I can fit more plates in there. And then if you look at the original term, where it was length divided by height equivalent to a theoretical plate, you're left with a very big efficiency gain. And so what this is sort of trying to drive the point home. Again, if you look on the bottom column, you can see that the non-monodisperse material, the analytes have to take a fairly tortuous path through the column. And so this is trying to show that the same analyte, 3 of them basically, and you can see that as it goes through the column, your detector recognizes a peak. But you know, one of those analytes took a little bit longer to get through around the particles and inside and out of the particles. And whereas the evosphere, because they're monodispersed, the packing bed is very uniform. And so what that means is you get tighter peaks. And so what does that mean chromatographically? Higher plates. We're seeing in some cases 60% higher plates. And you might say, okay, well, that sounds like an innovation from 2005 called superficially porous technology. And the real innovation here between the monodisperse particle technology and superficially porous technology is that the superficially porous technology has a sintered core in the side of it. So the surface area of the material is much lower, and so that can limit you when you try to load a lot on the column, or even trying to scale the method to a prep separation. Whereas the innovation here with the monodisperse particles are the fact that you can scale to prep, and also that your surface area stays very large. And so what that really means is the core shell materials are actually monodisperse. It's sort of the one benefit where they're really getting a benefit of the A term there. But again, as I said, the lack of surface area can come into play when you're looking to load more onto it. And so here, where the evosphere, it doesn't overload at 1 mg, 2 mgs, or 3 mgs per mil, you maintain your efficiency. In the core shell material, it tends to overload, or some of them tend to overload depending on the analytes and all these different things. So it's a real advantage that you have this increased surface area. And so going back to the resolution equation, you can see that the biggest impact to resolution is also, if you look linearly, like what's going to have the biggest impact. You can see selectivity has the biggest impact, but that increase in surface area also drives, optimizing your retention. So you get some real benefits there from your, improving your resolution. So what I would say here is, okay, I wanted to give a quick review. I go into a deeper review in part 1, and that can be easily downloaded on our website. But that was the quick review of the technology and why it's unique. I talk about the selectivity because we've applied a special bonding chemistry to the unique monodisperse particle technology that is allowing us, because of that increased surface area and efficiency of the particle, to get separations of oligonucleotides, retention of oligonucleotides, without the use of ion pair reagents like you would see with triethylamine and HFIP, or diisopropylethylamine and HFIP. So we wanted to partner with someone that is leading this charge, because HFIP, any of these fluorinated additives, are very toxic, and you have to be really careful when using these things. They're carcinogenic, they're toxic. It's sort of accepted that we're using it because this is how they always did it. But from now, I sort of looked at it like, hey, if we have a new material that can retain all these things more, and that they're highly efficient, well, I mean, I understand the HFIP isn't there for the MS signal, but what if I use a new material and applied it to this type of technology? So we partnered with the Copernicus University that's looking at this issue specifically. The experimental condition was using the evosphere max. The max indicates that it is a coated hardware, because that's important with oligos. They're very sticky. The column that we chose was a 1.7 micron and a 2.1 by 100 millimeter. The mobile phase, there's 2 different mobile phases. We have the unmodified oligonucleotides that are using in the range of 10 to 30% with methanol in 10 minutes. And then you have the modified oligonucleotides, which are using more of a 15 to 50% in methanol in 10 minutes. The temperature, where we've looked at 30 or 60 degrees C, flow rate is standard because we want to apply this eventually to an MS. The instrument we used was a Thermo Vanquish system, so very powerful, very sleek LC. We have the temperature in the auto sampler at 4 degrees C, and we're looking at a wavelength of 260 nanometers. But the point to discuss here is that this C18AR material has a C18 ligand plus a mixed phenyl character ligand on it. And the reason why methanol was chosen is because acetonitrile dampens pi-pi interactions. So when you're looking at oligonucleotides, you want to try to incentivize the oligos to retain on the column. And so if we would have used acetonitrile, they would have retained less. And so you're again going back to that selectivity piece is the key to resolution. That's sort of what we're looking at here, and that's why methanol was chosen. So the unmodified oligonucleotides, the nomenclature 20A, 20G, 20C, and 18HA. So the last letter there is the last nucleotide in the sequence from the 5' to 3' direction, and then 18HA is just all adenines. And then the modified oligos, this is the modified backbone. So you have DNA, which is an unmodified backbone, and then you have the phosphothiolated backbone. You have 2-O methyloxy as the modification using the DNA backbone, and then you have 2-O methyloxyethyl, which is a secondary modification. And so what they do is some of these modifications are to improve the half-life or possibly to improve bioavailability. Again, oligonucleotides are pretty much a new standard for drug products in pharma, and we're just looking at different ways to support the analytical workflow and for that matter, preparative workflow. So we looked at salt concentration, impact of salt type, and also impact of the salt pH. And salt concentration, we went from anywhere from 5 to 50 millimolar. The type of salt we used, we looked at ammonium acetate, ammonium formate, and ammonium bicarbonate, all worked well with the new column, and also the pH. We looked at pH 3, 4.5, 6, and 7.5. So when I looked at this, again, it's a compromise, right? Chromatography, if you increase one factor, you might decrease another factor. 50 millimolar, our intent is to move this to MS, the separation, because that's really what is the foothold in oligonucleotides where most of these separations are done is LCMS, but also for reaction monitoring, LCUV is very important. But 50 millimolar, we're getting needle thin peaks, but you can't put that much salt into your MS. We think we have a compromise around 15 millimolars where we sort of settled, or 15 to 25, depending on the application. And that was pretty much the case where there was a drop off between 25 and 10. So we think, around 15 is acceptable. Again, these things are pretty difficult to work with. So the fact that we're getting this type of signal is really exciting. The type of salts we use, for depending on which modified or unmodified oligonucleotide class you're looking at, the salts could be chosen differently. For this one, we settled on ammonium acetate because it had a pretty wide buffering range for the LCMS, and also did fairly well across the board. Again, looking at the retention, clearly if you have, it looks like, oh, well, pH 4.5 is the best retention, but actually pH 7.5 had really good results. pH 6 had really good results. So again, we sort of honed in on different pieces of this. So for the DNA 20 oligos, this is the 5, 10, 25. This is actually what it looked chromatographically. I feel comfortable, again, 10 to 30% methanol in 10 minutes. I think if you went with 15, you are really going to be humming at that point, and the mass spec can easily handle 15 millimolar ammonium acetate. That's something you guys do every day. When you look at peak shape for modified oligos, we looked at that 15 to 50% methanol. Most of the modifications did really well. The phosphothiolated ones, you could extend the gradient, you could increase the temperature to get them to act a little bit better, but really promising results with the C18AR. Very, very exciting. They're not flying through the column, they're being retained because of the pi stacking phenomena using the that we talk about in more detail. We're showing this data even though Copernicus University is looking to publish this in JChromA. We got approval to share it because of the fast track status that we think it'll have, and the exciting data that we're generating here. This is an unmodified sequence. The only thing to note at the end is that this is one sequence change at the end of the oligonucleotide. So you have 25 millimolar ammonium acetate, pH 6. Again, we're, for this specific one, we were looking at 12 to 20 methanol in 10 minutes at 60 degrees C. But you're seeing separation of one nucleotide change. That is amazing. And also, if what you see earlier around 1 to 2 minutes are the impurities in the process that were captured, and to know what those are, and the fact that they've been pulled away from the actual main peaks of interest is exciting as well, because that would be something that you could scale right to prep, and you have enough room there to just isolate what you want and shoot the other stuff out the back. Another thing here where the process impurities are pulled away from these is one nucleotide chain in the sequence. Again, pretty exciting. Enough separation. This isn't common. You don't normally see one nucleotide change, and this speaks to the power of the particle, of the technology used to pack the bed with this high surface area, high efficiency particle, and also the bonding chemistry chosen and selected. Plus then also using the coated column, so you get, right as soon as you're shooting your expensive Oligos onto your column, you're getting them right off of there, and you're not getting any passivation or anything like that needs to happen. Here in the red, I underlined it for the colorblind folks like myself. But again, you see a sequence of isomers where just one nucleotide changed and we're separating them. And some of the collaborators we've shown this are so excited about this. So that's why we spent 20 minutes just on this by itself. Then we looked at unpurified RNA oligonucleotides. So that's uracil instead of thymine, and it was desalted after the synthesis. And you can just see with 25 millimolar how tight for those that are working in this space, really exciting work. Really exciting that we're getting retention of these guys and separation. Normally you would have to use these ion pairs, and then you have to dedicate systems, and if you're dedicating systems, then your capital expenditures go up. And so this is really a game changer in that way, that if you can get at this analysis with ammonium acetate without ion pair, you're playing with fire. So, and another separation, just to show that if you extend the gradient, you can really even pull more stuff out. So we extended the gradient, and we went to just 15% methanol, but went out to 30 minutes. And then even the more polar compounds, 2 to 8% methanol in 30 minutes. So the whole purpose is, chromatography is really powerful. One of what I'd like to say here is this is the only separation where the peaks are actually in reverse. You would have to see one amino acid bigger. 3 is less, so that came out. 3 and 2 didn't quite separate, but we can again adjust the gradient, change the temperature, look at a different pH, look at a different mobile phase composition. But the fact that we're getting this type of retention is just really exciting. And so this is the 2'-O-methylethoxy separated. There was a little bit of peak shape issues. I think this was due to maybe an extra washing step in between injections could have been used to help. But again, you see the 3 peak 2 or sorry, peak 1, 2, and 3 are in the correct isolation order here. And so, yeah, we'll be having this will be published by JChrome A, hopefully submitted later this year. So the conclusions and future work, we have applied this new technology, which is the Evosphere Max C18AR, and we believe it's a viable candidate to evaluate potential non-ion pair mobile phase systems for modified and unmodified single-stranded oligonucleotides. And the point there is the fact that they're single-stranded. For future work, for larger single-stranded oligonucleotides, we have applied this bonded phase chemistry to a 300 angstrom pore size. So we believe that we will be able to handle even larger single-stranded oligonucleotides. We are evaluating Hillick in the monodisperse particle technology for very polar double-stranded oligonucleotides. We have a collaboration to look at how to improve the sample workup and sample prep using some novel technologies there. And then we have a solution for the standard approach. You know, if you're already using triethylamine and HFIP, or for that matter, diisopropylethylamine and HFIP, we have a C12 bonded phase. These ion pair mixtures can be pretty high pH, and so you need something that can handle the high pH. And usually you have to use fairly high temperature to get the stuff off the column, where the C12 can handle that in the Max hardware, but you need it in the Max hardware because you don't want to passivate these things. The oligonucleotides are so expensive that it just makes sense going with the inert coated hardware. And that's pretty much it. So what I'd like to do is set aside some time for questions. And if you have any questions about any previous work or future work, I'd be happy to answer it.
Thanks, Geoff, for that wonderful presentation. We have a few minutes to answer questions from the audience. Just a reminder that you can type any questions you have into the chat window, and please include your name and company. That way, if we don't get to all the questions, we can make sure to follow up with you after the webinar. So the first question, have those columns been tested with antibody drug conjugates?
So we're looking at this. We have, so you need wider pore sizes to handle that. The 300 angstrom material just came out. So to say, have they been tested? Not at this time, but we have another brand of products that is used specifically for that application that gives excellent results for the ADCs.
Okay, so maybe we can follow up with them after.
Yep.
Have you tried ion pair mobile phases with the C18AR column?
So that was, so we gave the one column. We actually, the original study, because we weren't sure, we know that the pi character was what we were going after. So the original study actually had us look at the Evosphere diphenyl, the phenylhexyl, and the C18AR. And then once we went to the C18AR and chose that, we wanted to then say, oh, well, how would it look on with the ion pair? But we didn't want to stop the work to then take this on to the MS, because that was where we sort of left the work. So we've gotten another, because we chose the C18AR, we've gotten another column, and the thought is that we will be looking at it with ion pair. Now, for that matter, the C18AR upper limit pH is around 8. So, you know, the ion pairs can be 8.5, 9. And so, you know, if we will look at it, but for optimum lifetime, I believe the C12 would be for more, let's say, rugged use. But if it's just for research, the AR might do really well there. I have seen in the past that ion pair does dampen pi-pi interactions as well. So from experience, I would say that I would lean towards a C12, but it's something we are going to look at.
Okay, that is all the time we have for today. If you had a question that we did not get to, we will follow up with you via email. I also wanted to remind everyone that we will send out a link to the recording of this webinar as well as the slides. Thanks again, Geoff, for a terrific webinar. This concludes our webinar series on monodispersity. We hope everyone was able to learn more about this significant innovation in chromatography. Thank you all for attending and have a great rest of your day.